Okay, our third and final proof lesson, and it's my favorite, proof by mathematical induction. This is like the domino proof, the domino proof method, in that what we're trying to do here, in a nutshell, it's going to be, we're going to have to do an example and go through the steps, but in a nutshell, we're going to be asked to prove some statement is true. Some statement is true. Okay, so this equals this for n is greater than or equal to 1 or something like that. So all integers n. And this is why it's called the domino effect. What we do is we prove with this. It's a three-step process. There's a basic step, in which case you prove true. You prove true for the smallest value, right? So all you do is sub n equals 1n and show that the statement is true. This equals this. Then the second step is called the assumption step, and you assume the statement's true for some n equal to k. We're going to write all this out again, don't worry. For some n equal to k, just some value in our if you can just imagine a lineup of dominoes, n equals 1 is the first one that tips them over. We're assuming true, so n equals k, so the kth case in there somewhere, and we're just going to assume it's true. So we're going to sub k in here, and we're going to assume that that is true. And then the inductive step, what we do there is we algebraic. This is where all the algebra is. This is where it gets really, some of these get really densely and intensely algebraic. We prove it's true for n equals k plus 1. So we say, okay, if it's true at n equals k, we prove that it's true at the next one. And the combination of these three steps says that 2 and 3 essentially says if it's true at one value, at one domino, then it will knock the next domino over. Okay, in combination, then you go back to 1 and say, hang on a sec, but we proved it was true for 1. So if it's true for 1, and if it's true for a value, the next value is also true, then it therefore must be true for 2, for 3, for 4, and it's got this domino effect that takes you then through all the values of n, starting with 1 and going to infinity for all the integers n. So that's it in a nutshell. And I've got a little, I love dominoes. I've got a little domino demo for you, just to bring this all to life. This is what the proof by mathematical induction is. Okay, I love those dominoes. I love that spiral. Okay, so proof by mathematical induction. So it's a 4-step process. Okay, a four-step process. And each step is absolutely essential. So 4-step process. Let's go through them. Step one is 4-step process. 1. So the first step is the basic step. It's the basic step, and at this step you are proving true or showing true for. I'm going with showing rather than proving because it is really just a matter of, it's a fairly trivial calculation in most cases. So basic step is to show true for smallest value of, I'm going to say n because it's normally n is our variable that we're working with. So show true for smallest value of n, and I'll even say most often n equals 1. We're most often dealing with the positive integers. So we're normally going from n equals 1. It's not always the case, but it most often is. So that's the basic step. The second step is the assumption. So we assume, so it's the assumption step. Okay, and what we do at this step is we assume the statement is true. Assume the statement is true for some n equals k. N equals k where k is greater than 1, so at some point in our sequence, one of those dominoes. So I'm going to just pop, it's always the statement that we refer to. Show the statement is true. Okay, that's 2. 3 is the big step. It's the inductive step. And it's, once you've assumed the statement is true for some n equals k, you need to prove the statement is true for n equals k plus 1. So if it's true at n equals k, then this third step proves that it's true for the next value, and that is the crucial step. And 4 is a final statement which you really just need to write out word for word. You just need to remember it. It's always worth a mark, and it's one of those just learn a paragraph. We'll get to that. Okay, so let's do an example and go through each of these steps very carefully. Okay, away we go. All right, the fun starts now. So step one. I'm going to write this out very methodically. Step 1, we're going to prove true. So you can see we've got a statement here. The left-hand side is right here, left-hand side, and our right-hand side is that little itty-bitty statement there. So we want to prove that the left-hand side of this 1 plus 2 plus 3, this looks like an arithmetic sequence, doesn't it? The first, what have we got in terms of an arithmetic sequence? 1 all the way up to 1, 2, 3 plus 3, 2, 1 equals n squared. So it's all the way up and all the way back. First n terms and then all the way back is equal to n squared. Okay, so we want to prove true for n equals 1. Okay, so it's well, this is super trivial because the left-hand side at n equals 1, it's just that first term there. Left-hand side equals 1. We don't even have to enter anything. Left-hand side equals 1. The right-hand side, we're entering n equals 1 in here. So that's equal to 1 squared, which equals 1. You're always going to have success here at this first stage, and you're always going to get a mark for your trouble. Okay, then we go to step 2. You'll find that with these induction questions, students are often a little fearful of them, but then you're very quickly into it, and just once you're started, it takes on a little life form of its own. So they're not so bad. Step 2, as I think they're fantastic fun. assumption step, excuse me, assume that the statement is true for some n equals k. So at this step, we just go assume statement is true for n equals k. All right, so what we're going to do here is we're just going to rewrite this thing. We're going to write it as 1 plus 2 plus 3 plus ding 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 k minus 1 plus k plus, and then we go to k minus 1 plus 3 plus 2 plus 1, and we're going to assume that all that is equal to k squared. All right, done. Now we're up to step 3. And this is the step, the inductive step, where we prove statement is true for n equals k plus 1. So this is the meat of it, right? This is where it all happens. So we've had the basic step, the assumption step, and now we're on the inductive step. So we're going to prove this statement is true. We keep going back to that statement at the top. And what it says is, right, for n equals k plus 1, 1 plus 2 plus 3 plus ding 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 plus, now wherever n equals, wherever we see n now, we put in a k plus 1. So k plus 1 minus 1, so that's k plus k plus 1 plus, now k plus 1 is going in there, back to k, plus all the way down to 3, 2, 1. And we want to show that that's equal to k plus 1 all squared. Right, now if we study this statement here, we're going to bring in our assumption. We're always going to bring step 2 into play here. That's the first thing we're going to look to do, because I've got k squared that's equal to all this here. So I need to find out where this is in my k plus 1 statement, okay? And it's not too hard to find. Now, if I just to help, I'm going to write what's the term before this k here? So we're going up. So this term before is a k minus 1. So I'm going to pop him in there actually. All right, he's there. I just didn't write him before. I just didn't write him. Right. So you can see that all the way up to here, where I'm just going to tick them off. Right. So I'm all the way up to k minus 1 and k. I'm done. Okay. I don't have this k plus 1 up here. And I don't have the k, but if we have a look at the next term after this one, we're now reducing by 1, so it's k minus 1. And I've got that k minus 1 all the way down to 3, 2, 1. I've got that k minus 1 all the way down to 3, 2. So everything in here, so what I can do now is I can say that this left-hand side is equal to k squared, because all these terms here, all these terms here are found in here except for this k plus 1. All right, and this k. Those two terms are they're the two terms in this expression that aren't there. So I can say that my left-hand side is equal to k squared plus k plus 1 plus k. And that's equal to k squared plus 2k plus 1. And hold on a second. If we factorize here, I've got k plus 1 squared, and that is my right-hand side. So I have been triumphant. Step 3 done. That's the inductive step done. And step 4 is just my evaluative statement, my final statement. Step 4 is my final statement, and I'm going to just copy and paste it from the book, and we're just going to learn it. Okay, so this says since P1, we can write that as since n equals 1 was shown to be true, or since the statement was shown to be true at n equals 1. That might be better, so we could get rid of that. Since the statement was shown to be true at n equals 1. And it was also shown that if the statement is true for some n equals k, it is also true for n equals k plus 1. So that was the inductive step. The assumption was made that n equals k, and then the inductive step proved that if it were, then it's also true for the next one. It follows by the principle of mathematical induction that the statement is true for all positive integers. That's the most succinct way of writing this thing. So since the statement was shown to be true at n equals 1, and that's just what you need to write for step 4 to get yourself full marks in this question. Okay, so just to recap, we prove it's true at the lowest value. Done. Think of that as the first domino. The assumption is an important step. Step 2, we assume it's true for some value of k. So we just write it up. And we just assume it's okay. And that's one of those dominoes in the middle there somewhere. Then the inductive step, we prove it's true for n equals k plus 1. We always write the statement out now with k plus 1 in for n. We build in our assumption and we do some algebra and we show that the left-hand side equals the right-hand side. What we've done there is very powerful. We've said that if it's true at some value of k, it's going to be true for the next one. So that's the domino, that's the knock-on effect. We proved it's true at n equals 1. So that means if it's true at the very first value, then steps 2 and 3 also say it's true at the next one. It's true for n equals 2. And if it's true for n equals 2, steps 2 and 3 say it's true for n equals 3. And so on right through. So that's this statement here just concludes that, talks through that knock-on effect, and completes the proof by induction. Let's do another example. Okay, so now we're going to use mathematical induction to prove that 11 to the power of n minus 6 is a multiple of 5, regardless. Now you see, we're proving stuff here. This is exciting. So step one. Okay, do as much of this as you can, but also the steps are really important. You've got to write this stuff out. So we're going to show true, right, to prove that, we're going to show true for n equals 1. Now it doesn't say what here is, but we should say for all n in the positive integer set. Show true for n equals 1. So, okay, that's all fine. Left-hand side equals 11 to the power of 1 minus 6, which is equal to 11 minus 6, which equals 5, which equals 5 times 1. So therefore, it's a multiple of 5. Okay, so that's good. Step 2, we're going to assume the statement's true for n equals k. That means that we're going to say that 11 to the k minus 6, some value of k, is equal to, now how do I write is a multiple of 5? Well, it's 5 times something. I'm going to use m, where m is an integer. So 11k, that's how I write 5m. So if m's 3, that's 15. Well, that's a multiple of 5. So that's how I write is a multiple of 5. Okay, that's the assumption. Done. Let's go to step 3. Inductive step. Prove true. Prove statement true for n equals k plus 1. Okay, so i.e. we need to prove that 11 to the k plus 1 minus 6 is equal to 5 times some other number, right? We've got to use something else. We can't use m. 5 times something else. 5 times n. N is an integer. This is what we need to prove. But we're going to use this. We're going to use this. Okay. Right, so how are we going to do it? Well, let's get to work. Left-hand side is equal to. So we're working with this. We're working with this, and we're trying to build in this guy here. Right, so how can we do that? Well, 11 to the k plus 1, there's some relationship there. 11 times 11 to the k minus 6. Would you agree? The left-hand side is 11 times 11 to the k minus 6. Okay, now that's quite close to this, but what I might need to do is bracket that guy in there like this. All right, so that's 11 times 11 to the k, but that's actually minus 66. So I need to add 66 and subtract 6. Okay, so that's 11. Now 11 to the k minus 6, I've now got that guy there is equal to 5m. So I'm going to write 5m in there, and this is plus 60. Okay, now what I need to do to get it looking like 5n, I need to get 5 out as a common factor. So now if I take 5 out here, I can say I've got 11m in here plus 12. Now, is 11m plus 12 an integer? m is an integer, 11 certainly is, and 12 is. So that's an integer. So I can say that that's now equal to 5n, where n is an integer, and that is the right-hand side. So step 4 is this statement here. Since the statement was shown to be true at n equals 1, so we take that and we copy it. Copy and paste. Except we're going to write, since the statement was found to be true at n equals 1, it was also shown that the statement is true for some n equals k. It is also true for n equals k plus 1. It follows by the principle of mathematical induction that the statement is true for all positive integers. And we are finished. Let's do another example. We need to do a few because there's a few different types. I'm going to do a couple of different types so that you've seen them, and then when it comes to doing your own questions, you might have some sort of guide. Okay, this example is a little more pleasing in that it's written out properly. Use mathematical induction to prove that 3 to the power of 2n plus 7 is divisible by 8 for all n in the natural numbers. This means natural numbers, and natural numbers are the positive integers. Right, that's the same as positive integers. Okay, so I'm gonna ask you to pause the video. I want you to try and do this one yourselves. Go through the steps 1, 2, 3, 4. It's very similar to the question above, but just get the structure, get used to the structure. Write it out, do the best you can, and then then maybe play this video out just to check that it all sort of matches up what you thought and clears up any issues. Okay, so let's get this thing proved out. So step 1 is to show true for our lowest value. So that is for n equals 1. So the left-hand side equals 3 to the power of 2 plus 7. And that's done. Step 2, we're going to assume so k plus 1 goes in for 2 now, so that becomes 2k plus 2. And we need to prove it's equal to 8 times something. So now we get to work on that. It's the left-hand side equals. You can see what I'm doing there. I'm forcing that. I'm forcing this expression here in here, so that I can draw on. I can draw on this. So that 8m is now going to go in where you see the 3 to the 2k plus 7. That 8m goes in there, you see. But I've got a little bit of work to do here, haven't I? Because what I did was I did 9 times 3 to the 2k, which is good for that, but 9 times 7 is 63. So I'm actually going to subtract that 63 to nullify it, and then add the 7. So that's the same as subtracting 56. Now that's a nice number because I know it's a multiple of 8. So taking the 8 out, I'm going to end up with 9m minus 7. All right, which is equal to 8 times n, where n is equal to this 9m minus 7, which is an integer, since m is an integer, you see. All right, so that's equal to the right-hand side. And so we have proved it. So step 4 is just again to copy, and it's a shame you can't do this in an exam, paste. Since the statement was shown to be true at n equals 1, and that's all done. Okay, I think we can do now, what is our exercise? Exercise is 1G. Let's get some practice at proving by mathematical induction. Cheers.